Welcome to our second lectures on the Statcom on fax devices. We shall continue with the point we have left in a previous section. So, we shall continue with the operation of the Statcom. So, by using the multiple pulse or the multi-level structures and the output voltage distortion and the capacitor current can be reduced to a desired level as prescribed by the different standard like IEEE 519, 514, this kind of standard, and it depends on the which voltage is connected. So, there is a different voltage level depending on the different regulatory condition will be there, and that is also the actually case of the investigation of the researcher. So, what kind of multi-level PWM structure will be more suitable in economic for the particular requirement of the Statcom, as well as the what kind of PWM technique will be also suitable. Thus, Statcom bar generator employing a perfect voltage source converter and that produce the sinusoidal output voltage and would draw the sinusoidal reactive current from the AC system and 0 input current from the DC capacitor theoretically, but it will take the ripple current and the losses. So, there will be exchange of the power between the converters. In practice, that is what I am saying, due to the unbalanced and the imperfection, maybe the value of the inductor is little different. So, there will be a, for this reason there might be imbalance, and even there might be a source unbalance. We actually tolerate some amount of the source unbalance as well as the economic restriction. This ideal condition is not achieved. So, there is a real power exchange between this Statcom and the power system. In practical converter, the semiconductor switches are also not lossless, and therefore, the energy stored in a DC store must be used to feed those losses. So, the losses incurred, switching losses incurred by this actually the Statcom has to be fed from the DC source. These losses can be supplied from the AC system by making the output voltage as a converter lags the AC system voltage by a small angle. In this way, what will happen? The converter will absorb a small amount of the real power from the system and will generate or replenish its internal losses and keep the capacitor voltage at a desired level. So, this is a way of actually achieving and feed the losses, and the Statcom also possible to keep the converter with the DC source. Nowadays, it is possible with the battery, super capacitor and superconducting magnet and all those things. So, that can feed these losses. In this case, converter can control both active as well as the reactive power of the system, and thus it is a function as a static synchronous generator. So, nowadays actually it is one of the point of investigation of this kind of topology, because you know we have a solar panel that can be fed into the with the Statcom, and thus it can inject also the real power. Capability of the controlling the real power as well as the reactive power exchange can be used effectively in application requiring the power oscillation damping. So, we have discussed that how actually power oscillation damping can be achieved by SBC. Same thing can be done with the Statcom, and it is more effectively damping, leveling peak power demand and providing uninterrupted power to the critical load. These are the advantage of it. Now, see that this is actually the schematics of the Statcom. So, generally we require this couple inductor, and this inductor and the transformer has been coupled to the coupling transformer, and it is connected to the point of common coupling, it is called PCC, and this transformer is required because the device rating may not match the system rating. So, for this reason we require to reduce the voltage level, and this is basically a current control voltage source converter, and what happened, we require to have a DC link voltage, and DC link voltage may be fit to the energy system or the solar system. So, that will basically acts as a synchronous generator, Statcom with the storage energy devices. So, nowadays this is actually put into the practice. Now, let us again discuss and revisit. So, what is the locus of operation of the Statcom? To exchange the real power with the system, there is a phase shift created by the converter output voltage and the point of common coupling. So, for this reason what happened, if the real power to be absorbed to the V0 and it should be actually lead V, and if real power to be absorbed from the system, then it should lag V. So, for this is the location. So, this is VSC and this is ISC, and in this zone you can see that in the first quadrant it supplies. So, actually it supplies P, it supplies Q. In second quadrant what happened? This is basically I and V, and thus in this quadrant voltage is negative. So, for this reason it absorbs P, but it supplies Q. And same way here in third quadrant it absorbs both P and Q, but in this case it supplies P and absorbs Q. So, total 360-degree operation is possible, and accordingly you can choose the operating condition of your system. Thus, Statcom can be operated as independent control of the reactive power. That means it can be operated in fourth quadrant operation. This is the flexibility when you put it with the storage element, its capability enhances. So, let us see that how Statcom can be controlled. For analysis of the controller, we consider that these devices are made of GTO because it require a full control devices, and in maybe for the lower rating we can use IGBT. The getting command of these devices are generated by the internal converter control in response to the demand of the reactive or the real power generations. The reference signals are provided by the external or the system control, which is determined by the functional operation of the Statcom. The main function of the internal control is to operate the converter power switches so as to produce the synchronous output voltage waveform that forces the reactive and the real power exchange. So, this is actually the way of controlling the Statcom. So, let us go to this actually the block diagram to understand it better. The internal control performed by computing the magnitude of the phase angle as required by the IQ ref and IP ref. This is actually IP ref and IQ ref that has to be computed by a processor dynamically. By generating the set of the coordinating timing and the getting pattern, which determines the on off period of the switches. Let us see that. Then actually you have a voltage, and thus you will actually go to the stationary frame. So, thus you generate this actually the output voltage and alpha. From there actually you calculate the switching sequence of these devices, and you give it to the converter and your energy storage devices, and thus actually your I0 will be IP plus IQ. You see that how much real power and the reactive power generate, and how much also the voltage is required to be generated, because you know that you require different level of the voltages to compensate reactive power and the real power. Now, how you do the internal control? Internal control can be achieved by the following way. Indirectly, by controlling the DC capacitor voltage. You can change the DC capacitor voltage, but generally DC capacitor voltage cannot be changed very fast because of its inertia, and thus in turn it is controlled by the angle of the output voltage. Or the second option, directly by internal voltage control mechanism, that means the modulating index, there you can change the PWM. So, PWM value you can control. From there you can change the terminal voltage, which in case of the DC bus is kept constant, and generally we prefer the second one because it is in a first in operation. The input of the internal control are the AC system bus voltage V and the output current of the converter I0 and the reactive reference current IQ ref. These are the feeding information, accordingly you will calculate the PWM. Mostly this technique is used. So, let us see. So, voltage V operate at a phase lock loop that provides the basic synchronous signal theta. So, you have to have a PLL. So, the PLL will generate, gives you the information about the theta. The output current is decomposed into the two component, real and the reactive power, real and reactive component. The magnitude of the reactive component is I0q is compared with the reactive component of the IQ reference. The error is thus obtained provides a suitable amplification of this angle. Generally it is nothing but a PI controller. So, the PI controller will generate this del alpha, which defines the necessary phase shift between the voltage and the current. This is the principle of the operation, and it will be del alpha will be added with the theta, and thus net angle will be theta plus alpha del alpha, and that will be given to the get firing logics. The angle del alpha is sum up to provide theta plus del alpha, which represents the desired synchronizing signal to the converter to satisfy the reactive current reference. The input signals are the bus voltage V and the converter output current I0 and the reactive current reference IQ ref and the DC reference voltage VDC. This DC voltage reference determines the real power of the converter and must absorb from the AC system in order to supply its internal losses. The converter output current is decomposed into the reactive and the real component of the currents. This component are compared to the external reactive current reference and the internal real current reference derived from the DC voltage of the regulation loop. So, this is the way you will actually control the Statcom. Now, see that. So, this is the reference I0. So, I0 will be splitted into the real and the reactive power, and thus you have a I0q and IP. So, I0q you will compute that what amount of the reactive current required to feed. Thus, you will be actually compare this I0q with IQ reference, and you will feed it to the error amplifier. It is essentially a PI controller, PID of PI controller, and output of the PI controller essentially compute the alpha or del alpha. But what happened? You also require to maintain the DC bus voltage, because you have to feed the voltage also. For this reason, you have a VDC minus VDC ref. From there, actually there will be an error signal. That error signal will be compared with the real component of the IP, and it will also feed to the error amplifier. Generally, it is a different error amplifier, and this output of this to fed to this actually magnitude and the angle computing block of this processor. From there, actually it will generate alpha and it will generate V0, and alpha will be added up with the actually the PLL. So, effectively this angle will be the theta plus alpha, and that will be actually fed to the get signal logic to fire up the GTOs or IGBT. So, after suitable error amplification, the real and the reactive power current error signals are converted into the magnitude of the angle. You may have also a lookup table. and from which the appropriate gate signals and in proper relationship with the phase lock loop is provided as a reference to triggering the circuit. So, what is the characteristics of the Statcom? Statcom can be considered as a synchronous voltage source which will draw reactive current from the AC system according to the external reference, which may vary in a defined time range between the same capacity when the inductive maximum and independent of the system voltage. So, it is a very effective tool when you have a sag occur, all those things. We shall see our next class that the this reactive power compensating capability decreases in case of the SVC for in transient and other condition, but it can compensate the reactive power very well even in a disturbed system. So, what we can conclude, what is the characteristics of the system? Losses in the Statcom are neglected, if we neglect definitely, and Statcom is assumed to be a purely reactive. Same like SVC, the negative current indicates capacitive operation, while the positive current indicate the inductive operation. This is the same convention we will follow. It is also have a low voltage limit of 0.2, that is quite important features of the Statcom, at which the converter still would be able to absorb necessary real power from the system and supply the losses, and thus can compensate the reactive power. The limit of the capacitive and the inductive limit are symmetric, and that is plus minus I max, that is provides the limit by the switches, mind it. So, thus this is the characteristics of the Statcom as we have discussed in case of the SVC. The positive slope BC provides for the VI characteristics to prevent the Statcom hitting the limit often and allow the parallel operation of the more than 2 units. So, you can put more than the 2 unit if the power rating of the Statcom cannot meet that particular area. So, you can put into the cascade band. The reference of the voltage Vref corresponds to the 0 current output. So, this is basically the 0 current output, until now it can actually go to the operating. So, it can go to B to C, and in this zone it can compensate, and thus you can increase this limit by paralleling putting the more Statcom. Now, dynamic responses of the Statcom is better compared to SVC. Why? Due to almost negligible transport loss or transport lag. Generally, it is most faster than that of attainable with the variable impedance, because capacitor will have its own inertia, and we also know that we want to have a transient free operation that we have discussed. So, we have a specific time of switching. Here you can change this dynamics by changing the modulation index of the PWM, and thus it is quite faster. It is also helpful that the higher power transmission application, the voltage source converter, for the variety of the technical and the economic reasons are multipulsed. Why? Because you can reduce the TST. We know that actually if you have a 6 pulse converter, then it is actually 6n plus minus 1 will harmonic content, and thus you make it 24 pulse. So, you definitely eliminate the higher actually higher strength lower order harmonics. So, it is for this we prefer for the harmonic consideration we prefer the multipulse converter. The small transport lags a wider frequency closed loop bandwidth, which provides a stable operation of the Statcom over a wide range of variations of the AC system possible than the SVC. So, it is quite superior than SVC. Please see the characteristics of the Statcom. So, this is a percentage loss, and we have considered this reference is taken from the Hingorani and Gyugi's books. This is a 100 MVR and 48 pulse converter. You see that this is the total losses, this is the converter loss, this is basically the magnetic loss. So, total loss essentially is the sum of 8 constituent 6 pulse 2 level converter of the multi arrangement. So, see that this is the power rating. So, how this losses actually changing. So, this is basically the 0 voltage operation, this is 0 current operation here, and here it is actually plus MVR and here it is a minus MVR. So, it can compensate both actually inductive as well as the capacitive. Converter losses are due to the semiconductor conductions, switching losses as well as the snubble losses and dVdt and dIdt losses. So, converter loss at low switching frequency will be less, about 1/3 of the converter loss due to the semiconductor switching losses, the other 2/3 due to the conduction loss, please mind it. The total magnetic losses are due to the main coupling transformer and the interference magnetics, and these are hysteresis and the eddy current losses. And main transformer losses of course are non-avoidable in high voltage applications. So, let us now come into the important point. This is called hybrid Statcom. A hybrid Statcom can generate or absorb same amount of maximum reactive power, or it has same control range of capacitive and the inductive output. So, it can work in either directions with the same power rating. Many applications may call for a different VAR generation and the absorption range. That is one of the practical consideration we have to keep in mind while designing the Statcom. So, it can simply achieve by combining the converter with either fixed or the thyristor switch capacitor on the reactor. So, it is a combination of the Statcom and the SVC. So, for this it is called the hybrid Statcom. This arrangement can generate excess in VAR of the rating of the converter and shifting the operating point into the capacitive region. So, essentially most of the cases energy fed into the drives, thus it is inductive in nature. So, it required to feed the capacitive VAR, and thus this kind of arrangement is getting the attention as well as the popularity. So, for this reason what happened, you see that this is a Statcom part and parallelly you actually connect a capacitor, mechanically coupled capacitor maybe, or the fixed capacitor or different kind of HVC. And that is what happened, this region will shift, you can compensate more the inductive current by feeding more capacitive reactive power and less inductive power. So, Vmax is the maximum voltage that given by the rating, Imax is the rating comes from the devices, and Cmax is the maximum current. So, that will be an add-on of the Statcom, thus you can compensate, and the slope basically will be more steeper, and thus you can compensate more reactive power. So, similarly it is possible to move the operating point of the Statcom further into the absorption region by combining a converter and the shunt reactor. So, you have connected a series, so it will be coming this side, and you have connected an inductor, so it will be coming this side. So, not much difference, just whether you are connecting an reactor or the capacitor, that matters. So, other things are same. Now, what is the advantage of the hybrid Statcom? Fixed capacitor and the fixed reactor shifts the operating point to a level. converter based on the VAR generation more or the capacitive or into the inductive region without changing the amount of the controlled MVR, but it just actually shifts the y axis, and it can be achieved by the thyristor switched capacitor or the reactor, but it will increase the total cost of the system. It is but obvious statement. Note that the addition of the fixed switched capacitor or admittance due to this converter based generation undesirably changes the VI characteristics of that of the output current, and output current becomes a function of the applied voltage. Problem lies, so what we have said that it can actually compensate at a very low power factor and all very low SAC and all those voltage. So, these features actually will be diluted if you use the hybrid Statcom, but you can increase the power handling reactive power handling capability of this transformer. So, again you can put, to balance it, you can have the Statcom, thereafter thyristor compensated capacitor, thereafter you can have a thyristor compensated reactor. So, accordingly then you can have a homogeneity, you can see that it is symmetric in a y axis. So, you can have a Vmax value where 0 current flows, and thus you can have the slope BL and BC, but it will be shifted. This is due to the essentially I Statcom max, thereafter IC max, and this can go this direction without any contributions of this IL max or IC max. Thus, both will add up and will give you the total IC max. So, this is the principle of the operation of the hybrid Statcom. Now, this is put into the operation very well because of its enhanced reactive power handling capability. Now, what else? Apart from the shift or the extension of the controllable VAR range, hybrid VAR generator arrangement, a converter with the fixed or the thyristor controlled capacitor or reactive banks may be used to the purpose of providing a optimal losses versus VAR output characteristics given application, because switching losses in this case will be lower. So, we can design optimally what will be the solution for it. Some portion which is dynamically changes will be in the Statcom and some portion can be fixed. This is a typical design problem for the fax engineers. Thus, let us conclude it. This is basically the hybrid Statcom with 1 PU TSR and FC. So, you will have, this is the basic range, and this is the losses and this is the TCSC, and this is actually TCR and TCSC where we will have a step changes, we have discussed it. And in case of the only Statcom, you will have this range of the losses, because you have to maintain little bit of DC bus voltage, thus it is not 0, and in both the direction it increases. And if you add FC, the fixed capacitor, so this curve will be shifting this direction, and it is in a operating only for that compensating the capacitive power. And if you put Statcom and TCSC, this part is for the Statcom, thereafter TCSC comes. So, this will add up this characteristics. So, thus this explains the overall characteristics with the hybrid Statcom. Thank you for your attention. We shall continue our next discussions with the more comparison with the SBC and the Statcom.